This, ladies and gentlemen, is an industrial 3D printer. So we can see layer by layer how this part has been created. That is also known as additive manufacturing. So we are moving under the SCORE model from buying to making. And in making, we're going to explore this technology in Module 8. Okay, so the learning goals are two. First, to understand the ways additive manufacturing could disrupt the manufacturing value chain. Here I'm underlining disruption. No more importing goods from far away, where you can print them at home, allowing a shift from mass production to full customization. And number two is to evaluate the impact that 3D printing will have on manufacturing and inventory management. Okay, so let us start. Let us first clarify the difference between subtractive and additive manufacturing. So here we have a creation from Michelangelo, to which he subtracted material, very skillful, in order to create what we call the David or David. And here we also have another David, but this David was created in the opposite manner. You can see here there is a scanner registering every imperfection, if there is any imperfection. All these features are registered, and then we can create and even modify that design as the one that we see here. Me personally, I still prefer the original, but hey, who is me to decide what is best? So we can be very creative and just modify. So this is additive manufacturing, and we have different materials, also known as feedstock. These are the raw materials. We can have solids, we can have powders or liquids. And because of these different raw materials, we have different techniques behind. So for example, whenever we're talking about solids, we have the fused deposition modeling, or also known as FDM. We also have the selective laser sintering for powders, or stereolithography whenever we are talking about liquids. So just to explore the fused deposition modeling, this is also known as material extrusion. So printers, they work by melting plastic through a nozzle and creating layer by layer. So they're building these components, these parts. Of course, you don't get to see this. This is just an illustration, but you can see with this nice robot the difference whenever we modify the layer height, which by the way is measured by microns. So 200 microns, that's 0.2 millimeters. Just to stop for a second, picture a millimeter. I think you know what that is. And now picture a 0.2 millimeter. So that is 200 microns. And if we just modify to 0.1, you can see clearly the higher resolution improvement. Now, here's also something interesting. This is a moving part. And you see here you have these kind of metal balls or spheres that helps to rotate this inner circle. And so that is a bearing, basically. So the way it is created is by printing layer by layer, and you also can create movable parts. So you print a layer, you stop, you continue, printer, you stop, you print, stop, back and forth, and then you continue like this, and then there is a separation, as you can see, and then eventually, because of the shape, this will allow to move back and forth. So you can create parts that are movable, mechanically speaking. So this is how the selective laser sintering technology looks like.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly upon the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength to fine features and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
All right, so aerospace parts, dental components. I know that there is a car, the Koenigsegg, that is having a turbine that is so complex to create it by the conventional manufacturing system that it is created by 3D printing because of its complexity. So yes, you can print metals. This is it's like science fiction, what it sounds, at least to me. So obviously the benefits of this technology is countless, and just to mention some, first of all, we can print components that are highly complex. So whenever you are applying CNC machining, it can get very, very complex to create certain parts now that you can 3D print them. You also reduce waste because of energy consumption, and you also reduce the cost related to inventory and transportation because you don't need to stock, you just print on demand. Yeah, like, by the way, some books on Amazon are printed on demand. They don't have them on stock. So this is kind of the same principle. So lots of benefits, and these are just some examples. Of course, these are prototypes still, but they are testing. So here on top, we get to see a bracket, a hinge bracket for an Airbus, and you can see how it has been optimized. And this is a titanium. And optimized means it keeps the properties of the specifications of strength, and yet with lower weight. And that matters because, for example, have a look at this one. Do you recognize what that is? If you have traveled by plane, of course you know what that is. That is a buckle that is used for the seatbelt. Now these are 3D printed buckles, and of course you see how they look. They still function, but they save a lot of weight. Imagine creating that by the conventional systems. It's too expensive, but with 3D printing it is possible. But here comes the beauty of this. A standard buckle weighs around 155 grams. With the additive manufacturing, the weight was reduced by 68 grams. And then you might say, well, you know what? If you put it on my hand, I don't feel the difference. Well, here comes the interesting part. Multiply that by the number of seats that an Airbus 380 is having, and you can translate into benefits of fuel and therefore CO2 emissions. So you see a little bit of weight multiplied by many, that's a lot of weight, and that's a lot of savings. So that just shows you these potentials. Now, there are some other consumer goods type of applications here on top. These are some shoes from Adidas. I remember this was still a prototype some years ago. I think nowadays it does exist. So they 3D print at least the sole, and this is just it is still produced in China. Here with this gentleman, well, it turns out that he had an issue with his skin, and he has these prostheses, and these have been 3D printed, so it can be personalized. And of course, as here I have stated, it gives back life quality. So you see different options, maybe different expressions he wants to have. So he can remove and replace like a spare part. More applications. Look, you know what that is? These are shoes, very fancy shoes. Maybe for your graduation, you can have something like this. You can wear that. That will fit fantastic. And I don't know, you can be on a kind of a movie of aliens or something if you also want. And that is actually a real collection from 2015 by a Dutch fashion designer, Iris van Herpen. And yeah, her inspiration was actually, I found this very interesting. She got this inspiration after she visited CERN, which is not so far away from Dornbirn, by the way. At the Large Hadron Collider. This is a place, this is this huge ring where they're colliding particles, and then these particles become little tiny particles, and this is just a picture that illustrates these kind of collisions, and it's just about finding where do we come from, and the little things that create the little things, and all. It's very interesting. I've never been myself there. So this is where she got her inspiration, and these are 3D printed. But again, I mean, the applications are just crazy. You can print chocolate, concrete. So this is a huge printer to print concrete. You see, you get to see the layers. You can print yourself. You get yourself scan and have a tiny little you and give it to your grandma as a birthday present, for example, so that she can remember you instead of a picture. There are more applications. You can also use mother cells, by the way, and then you can print ears, organs, hearts, a steak. How about that? And why not? Maybe a pizza in the future. And well, you might say, well, I prefer the traditional pizza, but hey, picture yourself, you're in space, and then you cannot order a Domino's pizza there, but how about printing a pizza? That comes very convenient. Or what if you're doing a spacewalk and then you just lose your tool? Well, you can print it out. All you need is a code. So you need the information of the item, and then you can print it, and of course the raw material to do that. So nevertheless, in spite of all this potential, it also comes with limitations, at least until now. And there are three big limitations. Number one, the options for the materials used to make the product are limited. Second, the size and quality of a product are also limited by the capabilities of the printer. So a lot of the examples that I showed you, like that building, is still kind of prototype. Maybe the building doesn't have the quality, the specifications that it should have in terms of heat transfer through the materials, or resistance, or it's just simply too expensive. It cannot meet the cost. 3D printing tends to be much slower than traditional manufacturing, at least until now. So it's okay to print a component for an airplane or for a kind of a super hyper sports car, but if you want to do that for a Volkswagen Golf, I think the conventional manufacturing is still a better option. But that might change in the future. It's just a question of how long it will take. So lastly, I guess the biggest, or one of the biggest benefits that we can point out is the so-called circular supply chain. So on top, you have the traditional transformation from raw materials, finished goods, until consumers, and sometimes you have the reverse logistics we talked before. Now we can have a truly circular economy, because the raw materials are now for the 3D printing. There's a consumption, a disposal, and these materials can be fully recycled and yet reused over and over. So now you have a very nice closed loop. 3D printing is one of the biggest components of Industry 4.0, so it belongs to this family. And there is a case that you're going to solve about this and the impact that is going to create for the supply chain for many industries. So that's all you need to know so far. Once again, thank you for your time and see you next time. Bye bye.